All right, I'm recording it. Hopefully, I will publish it tonight. Exam is gonna be next Tuesday in the lecture time, right? I'm not planning to give the whole 2 hours. Maybe it depends on the number of the question. We can make it like maybe 90 minutes something. I will finalize the question and then send you the announcements. We have the sorting and the searching included, except the red black trees. So that means whatever we cover so far. We see that the sorting is the first part we start because whenever we are searching, which is like one of the most common operation we do with the computer, right? Searching, we want to have the data sorted. Why? Because we have two options. Either we are doing the linear search, that means I'm finding every single element, checking every single element until I find it. If I cannot find it, I will return -1. The time complexity for the linear search was the ON because you start from the first element, you are looking for the element you are searching. That's going to be the number of comparison makes sense here. And for the linear search, I will be checking every single element. Worst case scenario, I see that I have ON's comparison and I couldn't find it. Binary search was great. I will be keep halving it. It doesn't matter how many sets of the data I have. I know that it is sorted, and every single time I check the middle element, get rid of the half of the remaining elements. So if I am keep dividing the number of elements to the 2, that's gonna give me the log n comparison, and I can find the elements. You already implemented it, you write the report, so everybody is clear about them. The idea was, I love the binary search, log n time complexity versus low n time complexity. I need to keep the data sorted. In the first place, I want to sort the data. We see that we have more than 100 different sorting algorithms. We will just cover the algorithms. It's gonna be, I wish this. First one was the insertion sort. We cover it because it's gonna be easy to implement one. The idea was we are starting from the second element and then comparing the elements with the left-hand side. If I find something smaller, right, I will be just inserting in between. The idea for the insertion sort, first, right, always keeping the left-hand side sorted. Second, if the left guy is already smaller, I don't really check the rest. This is my best case scenario. The third, if it is the smallest element, I have to shift everybody back to the next position. That is the worst case scenario. And we investigated the algorithm. I have 2 loops, right? The first one is for loop. I'm checking every single element. This one doesn't change. I have a while loop, depends on the condition. Again, if it is already sorted, I never enter the while loop. But if it is the reverse sorted, I will be executing this while loop for every single element. That's gonna give me another ON. That's why when I calculate the time complexity, I see that best case is ON, but the average case and the worst case is gonna be ON square. We solved them, right? So for the insertion sort, what do we remember? It's an in place. I'm not creating extra space. I will be just shifting the elements back and forth. And then the time complexity is going to be the second thing. You remember, best case, it is going to be ON. That's kind of like an exception. And then the worst case, average case, N square. Also, I will give you the list of elements. You are going to just apply the insertion sort. Loop invariance, we see that we are using it to prove the correctness of the algorithms. For the insertion sort, right, we have initialization. This should be something true before you start the loop. Maintenance is going to be remain true throughout iterations. And termination is supposed to be something I will be stopping the loop. Otherwise, it's going to be an infinite loop. In the insertion sort, we see that we are creating from the second element. That's going to be my initialization. Maintenance, always the left-hand side is going to be sorted, and then I will be checking the elements on the right-hand side. When I reach the last element, I will be terminating it. Don't expect any question from the loop invariants. Honestly, it was just like a brief information we shared. Then try to solve them. Again, if I give you the list of elements, I ask you to implement the insertion sort. Give me the steps, like what is gonna be array looks like after each iteration. Don't just write the sorted arrays. We see that when we are analyzing the algorithms, we will be checking multiple stuff, but this semester we will talk about the time complexity, the computational time, and then the memory usage. We don't really focus on the bandwidth, latency, or the other stuff. And we are calculating the best case, average case, worst case. This was the official calculation we did. But the long story short, I see that at the end, you just focus on the power of the n. The biggest power of the n is going to give you the time complexity of the algorithm. And here we see that if it is reverse sorted or half sorted, I'm going to get this number. So that's why I'm saying that O n square. Best case, O n. Worst case, n square. Average case, n square. And then we have the divide and conquer approach. Second algorithm, that is the merge sort. We use the recursion because it is easy to implement it, but remember, any algorithm that is recursive, we have the iterative version available. With the divide and conquer, we are dividing the big problem to the sub-problems and then solving the sub-problems, then combining them. We have seen two important divide and conquer approach, merge sort and quick sort. Remember their differences. Merge sort is sorting while combining it. So it is gonna sort it while combining. Quick sort is gonna sort while it is dividing. This is the major difference between these two. Merge sort says that just keep it divided to half until you reach the single element. Do nothing, just divide it, divide it, divide it. Once everybody is singled out, you will be combining in the reverse order. But while you are combining it, make sure that you are getting the smaller one first, then the larger one. Or vice versa if you are just sorting in the reverse order. So you will be keep dividing it to the half, half, and then once you are combining it, you are gonna just combine these two, and then the others, finally, the remaining parts. Recursive, right? We are applying the same thing for the left-hand side and the right-hand side, and then the merge part is gonna be, you see that combination sorting happens in the merge part. We even have the pseudocode reverse order, right? We are using the temporal location to swap it, but both of them is the same. The time complexity, it is always n log n. Why? Because I know that I'm keeping it half. There is no other option because I'm not like looking for the bigger one, smaller one. I'm just dividing it to the half. That's a perfect log n for keep dividing the data set to half. The log n is going to come from here. After that, I will be just combining these two by sorting it. I do that n times. I will be just like placing elements n times, and then it is going to give me the n. N times log n is going to give me the all the time n log n time complexity. Merge sort, it's also in place, right? We are not creating any other places. N log n time complexity for all of them. And then you will solve the data set with the merge sort. We see that when we are calculating the time complexity, right, we discuss about this pigeon versus the ADSL, which one was faster. We see that depends, but depends on the data size. Internet is going to change, but the pigeon is going to go always the same time. That's why the pigeon is the constant time, but the ADSL is going to be the ON time complexity. How did we come up with this? There are different ways that we calculate the time complexity, but we are using the simplest one, RAM model of computation, random access machine. Here, we are just like ignoring every single stuff, focusing on the efficiency of the algorithm. So the time complexity doesn't mean that it's going to take this amount of the time. We are just finding one thing, the number of computation and the relationship between the data size. If I increase the data this much, what is going to be the effect on the computation time? In that case, we just accept every operation is a simple operation. Everything is taking exactly one time step. When you take the 3/3, I see that that was a lie. Not every operation is going to be taking the same. Because in 3/3, we care about how it is executed in the computer. We focus on the hardware, how we can make these computations better in the computer. With the time complexity, you just assume that there is no such thing as the computer. We are living in the Middle Age, and then we are trying to calculate the efficiency of the algorithm on the paper. That's why we don't care. We don't know if the multiplication is going to take slower than the addition on the computer. Everything is just one step. Loops are not the simple operations because it is the way related to the data sizes. We will focus on the loops. Another thing, like we ignore the memory accesses. We don't care if it is in the memory or in the register. We don't have something like the algorithm, but in reality, we have. You will see that something inside the memory versus inside the register is going to be like 4,000 times slower. So of course they are not same. But repeating, we just focus on the algorithm itself, not the computer. And we will be finding the best case, worst case, average case. So if I have if and else statement, when you are calculating the code, there is an if else statement. Think about it. I have two options, right? Either I'm gonna calculate this part, I'm gonna compute this part. Is it possible that I will compute both of them? No. It is a branching, right? There is a condition. The condition is either true or false. If it is true, it is going to be block 1, false, block 2. So you will be calculating them separately. If you have the if-else statement, you calculate them separately. You find their time complexity separate. If I'm asking for the best case, you will get the minimum one. If I'm asking the worst case, you are going to say that, yeah, I'm going to be pessimistic. I will get the maximum one. That means if it is two separate blocks, we get the maximum one because we are calculating the worst case. If there is any type of the function call, what really happens when you call the function? You just go to the function place, calculate it, come back. That means I need to include the function's time complexity in the place that I will be calling the function. So you have the function call, you place the function's time complexity in the same place. And if we have the nested loops, we will be multiplying it. We go back to the insertion sort, right? I say that just focus on the loops. Same thing in the exam, same thing when you calculate the time complexity in the future. This is like the simplest version. Not academic, not stuff, but it is going to give you the easiest way to calculate it. Focus on the loops. This is a nested loop. That means you will multiply them. O(n, n square. But the best case, I never take the while loop. It's going to be just giving me O(n). And we say that we are trying to find the order of growth. That means if you increase the data size this much, how it is going to affect the computation, the execution. We are using the big O notation. This is going to give me the worst case time complexity. But in theory, right, in reality, we have big omega and big theta notations too. One of them is going to give you the average case, the other one is going to give you the best case. And then you will be officially representing like what is going to be the asymptotic tight bound or the lower bound for the lower case, the worst case, the best case, and the average case. This semester, I just focus on the big notation, and then I will be calculating the worst case. So for the merge sort, again, here it is like the time complexity. I will be keep dividing it half. That's going to give me the log n. And then the combination part, I have the for loops. It's going to give me the O(n), n times log n, and log n is going to come. Anytime when we have the divide and conquer, we will be usually implementing it with the recursion. And when we have the recursion, try to find out how the recursion is working. Like this guy is calling itself all the time one time, or this calling it twice. You will see that sometimes you will be just like getting the twice recursion. That's going to give me the exponential time complexity, like the Fibonacci. We will come back to that topic later on, especially when we discuss about the dynamic programming. These are the common order of growth when something is independent from the data size. We just call it constant time or one time. O1 is not means like it is super fast or it is nothing. We are not ignoring it. We say there is no relationship. It is just independent from the data size. If it is like same relationship, you increase this data this much, and then the increase on the computation is going to be the same amount, linear time or n. We have the n log n for the sorting algorithms, right? This is going to be the best case for the sorting algorithms. N squared is going to be the slower case for the sorting algorithms we learned. Exponential growth, that's going to be like every single data is going to double your workload. And log n is the binary search. We even have the fancy name for them. We don't say that O1, we say that constant time. Log n, we call it logarithmic time complexity. Or sometimes it is going to be like log n to the something. We say that logarithmic, whatever. But we don't really use it that much. We briefly say that logarithmic for many cases. Linear time complexity, quadratic, and polynomial is going to be n cubed, n to the 4. So we will be calling all of them as the polynomial. Or it is going to be exponential if it is like 2 to the power of n, 3 to the power of n. This is usually something that means that, hey, that's a horrible time complexity, not even applicable. So if I have two separate time complexity, I'm getting the maximum one. That means I have like the for loop here and then another for loop here, another while loop here. They're all independent. I'm getting their maximum. Because remember, we are pessimistic. We are focusing on what can go wrong, the maximum one. If we are multiplying it with any constant number, that's okay. We still try to find out the biggest power of n. In other saying that n equal 5 times n equal 100 times n, or n squared equals 100 square n. I just focus on the biggest power of that. But if I'm multiplying them, this is the nested loop. You have a loop here, and then inside it, you have another loop. It means for every iteration of this loop, you are going to just complete this whole loop one more time. In that case, you will multiply their time complexity. For the recursion, there are different methods that we are finding. Again, you focus on the recursion, how it is like going over. If every time it is calling itself once, or every single time it is calling itself multiple times, and what is going to be the data size for each recursion, then you will say that, for example, here, for every single time, I'm calling it for the right and the left subtree. The data size is going to be divided by half, another half. So this is going to be the logarithmic recursion, and it gives me the log n time complexity. I will give you like the code snippets like that. Ask you what is going to be the time complexity. You see that here, there is a for loop running n times, another for loop running m times. You can say that the time complexity, by default, this guy is going to run n times, this is going to run m times. You don't say that m plus m. You say that, hey, it is linear, depends on the data size. This is going to be the time complexity, and then there is no extra space usage. If you calculate the space complexity, this is the space complexity. I don't really ask your space complexity to calculate it for the code. I can ask the space complexity for the algorithms. Like insertion sort is not using any extra space. This is something you can get. Or here, I have the nested loop, right? This guy is going to run n times. How many times this guy is going to run? Starting from n, goes all the way to the I value can be 0. So this guy is going to run n times 2. N times n is going to give me n squared. Again, focus on the worst case time. How about this? Starting from half of the n, goes all the way to the n. I plus plus. What is the time complexity here? You can see that it is running n divided by 2. But remember, I just care about the power of that. N divided by 2, 5 times n, 7 times n, they are all O n. I'm going to say that this is the linear. Starting from 2, I don't care if it can start from the 200. It can go all the way to the n. But this part, you have to pay attention, how it is changing it. Every single time, I'm multiplying the j value by 2. So that means I can easily reach that location. J value is going to be 2, 4, 8, 16. That's like growing so fast. That's why the time complexity of the inner loop is going to be log n. Because if I have 1 million n value, this guy is going to reach that in 20 iteration. So that's going to be super fast. The time complexity of the for loop is going to be log n, and then n log n is going to be the thing. So when I give you the loops, first focus on the loop. Second, like look at them, where it starts, where it ends, and especially how it is changing. So I can say that it is less than n, it is less than 2n, it doesn't matter. But if it is less than n square, the time complexity is going to be n square. N square is different than like the 2 times n, 5 times n. Ignore the constant, but never ignore like the n square, n cube. That's going to be the time complexity. The second thing, how it is changing. Sometimes I'm going to keep divided by half, especially if it is like the plus, plus, minus, minus, it is going to be a linear change. But if I'm multiplying by 2, dividing by 2, pay double attention, it can be logarithmic. Here, I0, I'm incrementing how the I value is changing here. And it's going to be n divided by 2, n divided by 4, divided by 8. That's a logarithmic time complexity. Again, pay attention how it is getting growth, right? What is going to be the ending value? If it is 5 times n, 7 times n, it is linear. But n squared, n to the power of 3, that's not linear. That's going to be n squared, n to the power of 3. How it is removing, reducing, or increasing? Plus, plus, minus, minus, they are okay. Plus equal to 100, that's also linear. But if I'm saying that I times 2, I divided by 2, pay double attention, it can be logarithmic. And another thing, I'm not going to trick you this semester, just to keep in mind that we will be seeing a lot in the 330. When you are checking the length inside the for loop body, even if you think that that's going to be a simple ON, that's an ON square. Why? Because this part of the loop is also running n times, and every single time you are checking the length function is just like counting the number of elements. So the length function itself is going to have the ON time complexity, and then you have the ON here, n times n is going to give you the n square. That's why in 330 I will tell you that don't check the length inside the body of the loop. Check outside, assign it to the local variable, use it. What is the time complexity of finding the maximum or the minimum element in the given array? If it is sorted, that's going to be O1, right? It's the first or the last element. Not sorted, I have to scan the whole array, find the maximum or the minimum value. That's going to be the ON time complexity. So what is the time complexity here? I especially take this screenshot because it was one of the tutorial here. They say ON to the power of 4 because I have like the 4 nested loops. I have the 4 nested loop, that is correct, but it is going to be ON to the power of 8 because I am checking the length in every single iteration. Usually people ignore it. They say that I will just focus on the loop. But the rule is simple. If there is a function called, you replace the function's time complexity. The length function is a simple while loop going through first element to the last element, counting the total number of the elements. That's why if you make it, it's going to be a super amateur coding that will increase the time complexity for nothing. Then we discuss about the tree. We say that there is a hierarchy, roots and the leaves. We learn about the parent-child relationship. We say that if you have up to 2 children, it's a binary tree. And then the binary tree has a special version, heaps. I can ask, what is the heap, right? It has 2 properties. The first one is the order property, the parent-child relationship. If I'm talking about the max heap, every parent is bigger than child. If I'm talking about the min heap, every parent is going to be smaller than child. This is the order property. Second, structure property, it's going to be nearly complete binary tree. That means every level is going to be full except the last level. Last level goes from left to right. And then we decide which one is going to be heap here, only the last one. And how we are keeping the heap, this is different than the binary search trees or the binary trees, don't confuse. I just need a one-dimensional array. Because everybody is going to have a children, and then it is going to be always going from left to right. I don't even need to keep the data for the index of the child or the left. I know that if I have a single one-dimensional array, and if I'm keeping it in the heap form, the left child is going to be 2i, and then the right child is going to be 2i plus 1. I can easily calculate everybody's left and the right child. So by default, for the heap sort, there is like a 2 sections of the sorting algorithm. The first one, you build the heap. You start from the first element, you keep heapifying it, and then getting to the max heap. But I'm going to just give you the max heap or the min heap to start the algorithm from half. So you don't have to like worry about how can I do the building the heap part. But if I don't give you, right, if I give you the regular array, then you have to first do the build heap part, start inserting it every single time you replace the stuff. That is the first part of the algorithm. The second part is going to be max heapified. Heap is going to be always balanced because it's going to be a complete binary tree. The number of elements on the left-hand side is going to be almost equal to the right-hand side. That's going to give me the log n time complexity. Remember, with the trees, we love the balance. And then I can always say that it is going to take the same amount of the time. That's the reason the best case, average case, and the worst case is going to take n log n time complexity. And the heap sort, you see that the first part is going to be the build max heap. You are starting from elements, building it. After that, we go all the way to we have a single element. We are always removing the root with the youngest child because I know that the root is going to be the maximum one. I'm taking the maximum one, replacing it with the youngest child, then calling the max heapify. In the max heapify, you do one operation in each level. That's going to give you the log n time complexity. So everybody becomes the root one time. That's going to be O n time complexity. And then when you remove the root, it is going to be the max heapify log n time complexity because you do one operation in each level, nothing more. And you call the build max, right? You are getting it. You are starting from the youngest child. So this part, please pay attention. Don't confuse the build max heap part. This is not going to be needed in the exam because I'm going to give you already the max heap. But if I ask you, right, we were starting from the youngest family to build the max heap, to scanning all of them. And then finally, when you reach the root, it was the max heap. Now, this is the max heap already. I'm going to just like give you this. I will say that apply the max heapify. You are going to replace the youngest child and then with the root, then you will be calling the max heapify. You replace the youngest child with the root. Don't start from the bottom. Start from the root. And then you check every single layer one time. This is including the build max heap simulation. Let's first get the max heap, and then after that, here you see the 44 and the 14. always take the youngest child. Who is the youngest child? Bottom layer, rightmost. I'm not saying the smallest one. I'm not saying that the leftmost, rightmost. Bottom layer, rightmost is gonna be the guy you always replace it. So after I finish the review, we can solve one heap sort together, just to make sure everybody understands it. Then we learn the quick sort. This is also a comparison algorithm, a divide and conquer, different than the other algorithms. We are choosing the pivot value, right? In the quick sort, the most important guy is the pivot, because I'm gonna just compare the numbers according to the pivot and then replace them. All the sorting is gonna happen in the divide part. We don't do anything in the combine part. This is the difference between merge sort and the quick sort. And you see that when I'm partitioning it, I'm actually sorting it according to the pivots. At the end of each iteration, we are sure about one thing. We find the correct place for the pivot value. We have two index, right? One starting from the beginning, the other one is starting from the end, scanning it. They are meeting in the middle. When they met, they find the place for the pivots. We have 4, 5 different ways we can choosing the pivot. First, last, middle element, or the random element. I see that in the exam, you are free to choose first element, middle element, or the last element. Please don't say that I'm choosing the random element, because when we are solving it with the pen and paper, we don't have something called random. So you can choose first, last, or the middle element. And all of them has the problem with the worst case time complexity. It is going to give you the O(n) square. That's why we have the median of 3, median of 4, 5. And we say that this is how we are sorting it. Last element as the pivot. The problem was, if I keep choosing the smallest element or the largest element as the pivot, I'm hitting the worst case time complexity, because I'm going to get O(n) times choosing the pivot, and then every single time I keep it half, just leaving one element and then n minus one element on the other side. So the height is going to be also O(n). The time complexity is going to be 1 square. This is how we can fix it. Median of 3. So we are just trying to avoid picking the largest or the smallest element as the pivot. That's the whole idea about the median of 3, 5, 9, whatever. The time complexity, right? The worst case time complexity is going to be O(n) square. But the best case and the average case, it is going to be n log n, and which is a really good n log n. When we apply the median of 3, we guarantee that the worst case time complexity is going to be also n log n. Finally, we cover like the 3 different sorting algorithms. They were called sorting in linear time. They're not comparison, right? But they all have their conditions. The counting sort, it depends, right? If the given elements are in a smaller range, I can just apply the counting sort. I was creating a count array, first counting how many zeros, how many ones, how many twos I have, then updating the count array, placing those elements. It is stable. Everybody is going to appear in the same order. Second one was the radix sort, right? Mostly like the card sorting. Here, the important part, you start with the least significant digit first. Then you will have the sorted values. Bucket sort, idea was similar to the hashing, right? Hash tables. We were just splitting them into the buckets, applying another sorting algorithm to sort each bucket, then we combine them. Data structure, array was the linear data structure, same element, same type, same size, contiguous memory allocation. Reaching an element is O(n) time complexity, because I know the location easily by doing the pointer arithmetic to calculate it, but insert delete was costly, O(n). And we see that it is cache friendly. Linked list, Insertion deletion is easier because I don't care about the others. I'm just like inserting in between or removing the elements. But the access was ON because I have to start from the first element and then visit. Not cache friendly. Plus, I need extra space to store the memory locations of the next or the previous element. We created the linked list. We say that if I'm just storing the information for the next element, it is single linked list. Next and the previous one is going to give me the double linked list. Advantage, I can traverse in both location, backward, forward. Disadvantage, I will need one extra space. And if we connect the first and the last element, it is going to give me the circular list. Stack. Last in, first out, first in, last out. This is the first thing, right? Insertion and deletion is called push and pop. And I need just one pointer. That means I need to know who is top. That's all. Queue. First in, first out, last in, last out. And then I need to know two guys, who is the head of the queue, who is going to be the tail. I need 2 pointers. And then we see that when we are implementing the stack, we want to make sure that stack is not empty before we pop the stack. And we use the different data structures to implement them. I can ask a question like compare the stack and the queue. First principles, then like pushing, popping, or NQ, DQ, like what are the operations called, plus how many pointers we need to implement them. Hash tables, we discussed what is the best form of the data, right? We can keep it. So it is going to be always a one-time complexity to insert. We say that this is the direct access table. Everybody is going to have their own index number equal to something. But we discuss why it is not applicable because I need a huge storage and then I will be wasting most of those storage. Then we say that let's be more realistic. We come up with the hash tables. We have limited space and then we will be just creating some formula, right? That is our hash function. Hash function is going to give you the same location all the time. You compute and then you search. So what is the hashing hash tables? This is like the first question. Second, what is the collision? When two elements is pointing to the same location, there is collision. And then how we can fix it? We have collision, and then we have two options to fix it. Close addressing, another saying chaining. That means I'm gonna add extra memory, linked list, then I can solve it. In that case, the time complexity is gonna be O1 for the best case, ON for the worst case, because if I put all of them at the same place, it's gonna be the ON time complexity. It is all related to the hash function, right? If I have a good hash function, it should be efficiently computable and then uniformly distribute the keys. I can ask you what makes a function a good hash function, explain it. And then don't worry about all the others, like these was examples I showed you that we can use the division, modulo operator, hashing. But when we are limited with the space, we have to use open addressing. Close addressing, chaining. It's just like a linked list and then extra space is needed. Open addressing, I am limited with the memory. I cannot add extra space. And we will be using the linear probing, quadratic, or double. Linear, you hit the collision, it is already occupied, you check the next element. Quadratic, we are making the hash function a little bit more complex to reduce the number of collision. Double hashing, you have the first hash function, hits the collision, you run the second hash function. So if I'm gonna summarize it, first, what is hashing, hash function, right? Why we cannot use the direct access table all the time? What makes a hash function good hash function? Like it is gonna be always computed, giving the same name, efficiently computable. Second, it is gonna evenly distribute the numbers if possible. And then what is gonna be the solution for the collision? We have the open addressing, close addressing, probing. And finally, we discuss about the different types of the trees, binary tree, right? Up to 2 number of elements. We call it the binary tree. strict binary tree, or sometimes we call it the full binary tree. It is 0 or 2 children. And then we have the complete binary tree. That's going to be the all levels except the final level is going to be filled. The last level is going to go from left to right. Perfect binary tree, all levels, including the final level, is full. We are using it as an example, or we are trying to get closer to this example because it has the perfect balance. The first thing we learned, right? Tree traversal, pre-order, root left, right, post order, left, right, root, in order, left, root, right. What is the time complex of traversal? It is always O (n) because you are visiting every single element one time. It doesn't matter which order. So traverse is going to be important. After that, we discuss about the representation. We have two options. Either we are using the linked list or we are using two arrays. One of them is holding the data. The other one is holding the index of the left child and the right child. So finally, today we discuss about the binary search trees. Remember, the rule is simple. We have first the unique keys, and then we are placing the key. Anything less than key is going to be on the left subtree. Bigger than key is going to be on the right subtree. Then we figured out which one is the correct, which one is not. The question for the binary search tree, I'm going to give you the list of elements, and then you will be building the binary search tree. What is the time complex of the binary search tree? Equal to the height. If I have the balance, height is going to be shorter, log n. If no balance, the height is going to be very long, O (n). When you are insertion, deleting, right, you will be searching and then finding the correct position. Then every single time you insert, make sure you are inserting it as a leaf, newborn, not in between. And other than that, we can always find the minimum, maximum elements for all of them. Deleting, we have three options. No children, just delete it. One child, place the child in the parent place, delete it. Two child, we have two options. Either you are finding the maximum element in the left subtree or minimum element in the right subtree. And then it is going to be recursive all the way to you hit the bottom. We say that this is going to be the time complexity is always equal to the height. If we say that what is the time complexity of binary search tree, I don't care if it is balanced or not, it is going to be always height. If it is balanced, log n. Otherwise, it is going to be O (n). The tree sort, you see that since we are already keeping it sorted in the binary search tree, if we just apply the in-order traversal, that's going to give you the elements in the sorted order. And we have seen the time complexity. For the best case is okay and log n, but the worst case it is going to be n square and it has so much overhead. That's the reason the tree sort is not super popular. And the last thing we discussed, we see that when we have the binary search tree, we want to keep it balanced because I know that if there's a balance, time complexity is going to be log n. Any question? So let's check the sample questions quickly. But in this case, screen is not going to be recorded. I can even, okay, I will just keep it recording so it can record the voice. This is the examples I give the victory, right? There are merge sort and quick sort. I'm sure you can do them easily, check them. There are even tools that shows. I want to solve the heap sort together. So if it is already the max heap, right, I will be taking the root, replacing it with the youngest child. So algorithm is going to literally, when you reach to the max heap, this is going to be the first element and this is going to be the last element. Your algorithm is just swapping the first element and the last element. But when we are solving it on the graph, I will say that replace it with the youngest child. Not the smallest, not the minimum, youngest. Youngest means bottom level, rightmost. So this is how your heap is going to look like. It is going to have the 6 here, 43, 39, 11, 17, 28, 4, and 10. Now we will be calling the max heapify. I disturb the root. I need to go from the root, right? I will check 6, 39, 43. Who is the largest element here? Who needs to be parent of this family? 43. You will be replacing it. And I will do it step by step, actually. It's going to be harder, but 43, 6, 39, 11, 17, 48, and 4. Here it is going to be 10. Now you need to just keep track of it. 6, 11, 17, who is supposed to be parent in this family, this 3, right? It is going to be the 17. You just replace them. 43, 17, 6, 11, 10. Here it is going to be 39, 48, and no, not the 48, it is 28, and 4. So I reach to the max heap one more time. Correct? So I can take the 43. Let's put the sorted numbers here. First I took the 52. Now I'm going to take the 43. Replace with which guy? Youngest one. Who is youngest? Bottom rightmost, which is going to be 10. Let me continue here. I'm going to have the 10 and then the 17, 39, 11, 6, 28, and 4. So 10, 17, 39, who is supposed to be parent? 39. We replace it. 39, 10, 17, 11, 6, 28, and 4. Now between these 3, right, 28 is supposed to be there. You see that every single time I'm just like fixing it a little bit more. The last steps are going to be faster. Another max simplify here. You will be taking the 39, putting it there. Now, I will be replacing it with the youngest child, which is going to be 4. It becomes the 4, 17, 28, 11, 6, and 10. Start from the root to max simplify. 28 is supposed to be replaced, right? It becomes 28, 17, 11, 6. Here it is going to be 4 and 10. I need to also replace these 2. I will be just replacing here, limited with this space. So you reach to the max heap again. You remove 28. Take 4. 4, 17, 11, and 8. Here it is going to be just 10. 17 is supposed to replace. 4, 10, 11, and 8. Now I will replace the 11. 17, 11, 4, 8, and 10. So we will take the 17, replace it with the 8. Go to the next one. It's going to be 8, 11, 10. And 4. Eleven is supposed to take the place. 11, 8, 10, 4, another max heap. We replace the 11 here. Take the youngest child. That's going to be 4, 8, 10. 10 is supposed to take the place, right? It becomes 10, 8, 4. Take the 10. Replace it with the 4. 4 and 8. Swap them. It becomes 8 and 4. You remove the 8. Then we have the 4 left. That's going to be where the algorithm will stop. Any question? So just 2 things you need to be careful. The others are going to step. Always first take the youngest child. Always take youngest child. Second, after you take the youngest child, you start from the root because you disturb this family. You will start from this root and then you are going to just like follow one family at a time. You need to just swap one element in each level. This is usually where the people make the mistake. They are not either taking the youngest child or they are not starting from the root to heapify it. What was the best case, worst case, average case for the merge sort? It's always n log n. Quick sort, best case, average case, n log n. Worst case, n square. Heap sort, always n log n. And this is the sample exam, right? You are going to get some questions like that. Forget about the explanation. I don't need your explanation as long as you give me the correct n square and on. So here, this is what I'm talking about, like 2 times n. I don't care if it is 2 times n, 5 times n, it is n, because we ignore the constant. And it is incrementing linearly. So the outer loop is going to be on. Starting from 0, goes to the half. I can go to the half, quarter, it doesn't matter, 5n. It is incrementing linearly. Another n, so it's going to be on square. 0 n, that is going to be on. That's another on. They are independent, so I'm taking the maximum one, on. We just multiply them when it is the nested loop. Now, pay extra attention. It is n cube. It is not 3 times n. They are 2 different stuff. So this guy is starting from 0 to n cube. What is the time complexity of the other loop? It is going to be n cube because it is going to the n cube. Power is important, not the constant. Going from 0, 2 times n, 2 times n, 5 times n, 2 million times n, it is still OR. This guy is going to be n to the power of 4. Zero to n, linearly, that is on. 0 to I, j plus plus. Now we say that it is not n, I, but think about the worst case scenario, n becomes, I becomes n. That's why it is going to be the n square. In reality, it's not going to be never running n times, right? It's going to run like around n divided by 2 times. Same thing, it is linear for me. Starting from 1, n, but it is incrementing I times 2, right? Check the I values here, 2, 4, 8, 16. That's why this guy is gonna run log n times. So if you just give me these big annotations, that's gonna be enough. But pay attention how it is changing. And then if it is like the n cube, n square, or 2 times n. You can apply the insertion sort, quick sort, median of tree, merge sort, practice them. Heap sort, again, I will give you the max heap. You focus on it. Even if it is gonna make you feel better, I'm not even giving the min heap. Let's keep it with the max heap. So you study with the max heap only. The counting sort, remember we create the count arrays, and the bucket sort, we are just splitting them into the buckets. Radic sort, you start from the least significant digit. Let's do this. What was the best case time complexity for the insertion sort? ON. When it is already sorted. Worst case? When reverse sorted. Heap sort? The worst case? Same thing for merge sort. Because these two guys doesn't care if you are sorted, reverse sorted, they're already shuffling you and then applying the same thing. Quick sort. Median of 3. We are fixing that problem. How many different ways we can choose the pivots? 5. First, last, middle, random, and median of 3, 4, 5, blah, blah. Relationship between binary tree and the heap. Every binary tree is a tree. Every heap is a tree. Every heap is a binary tree, but a special type of the binary tree, right? With the 2 properties. This is like the binary search tree questions. I will give you the array. I see that first build the array, give you some points, and then you can insert, delete some extra in the following examples. Up to here, because we didn't cover the graphs, right? No graph data structure. Here, you can have like the explain, stack and the queue, properties of the max heap, compare array and linked list, compare single linked list, double linked list, advantages, disadvantages of the direct access table. This is what we covered. Good hash function, pre-order, post-order, implementation, policy, right? We have 3 rules: no child, 1 child, 0 child. And then we will be discussing the time complexity of the binary search tree. Remember to mention about the height. And then we didn't cover the red black tree or the others. So I can say that from 19 to 28 in the last questions, make sure you answer them. You are going to see a couple of them. Any question? Perfect timing, 2:40. You see, I'm always here on time, finish on time. So I expect the same thing from you. All right, good luck with